Paul from Allied Signal, engineer at the US Research Center.
Good morning. I'd like to begin by thanking the organizers for an opportunity to discuss with you some of the work that we've been doing using ethylene, primarily as a probe molecule. And what we've done is, in the process of using it as a probe molecule, we found that it undergoes some very interesting chemistry on a variety of supported metals, and that we think that this might be useful in finding alternative ways of characterizing supported metals, supported bimetallics, and things like that. Now, as Professor Softler mentioned, this work was done in conjunction with Mike Trineri at the University of Illinois. The bulk of the work was done by his graduate student, Shahar Mosin. Yes, can we have the lights now, please? What I have here is a slightly less idealized view of what a noble metal cluster might look like on a support. By less idealized, I mean it isn't just a circle, it actually has a variety of sites. And in this particular case, this is simply a platinum-38 cluster, and what you can see is that here you would have the beginnings of an FCC 111 type surface. Over in this region, you would have the beginnings of a 100 surface, and in between those, you would have things that if you wanted to call this, if you wanted to follow this line down, that would become some type of kink site. You have corners, you have edges, you have a variety of sites. And what would be very gratifying is if we could understand what kind of chemistry takes place at these sites, what kind of chemistry might take place at these sites, what is the role of the ridge between the various planes. Now, I'm not going to say that we can tell you exactly what's happening here, but what I am going to say is that I think we have an alternative for how we can begin to understand some of the properties here. Now, traditionally, the probe molecule, when dealing with infrared spectroscopy, has been carbon monoxide. And while there are differences in the carbon monoxide spectrum, depending upon the size of the metal particles, whether or not you have alloys present and that kind of thing, you typically really only see three, if you're talking about rhodium, or if you're talking about palladium, two different kinds of species. There's a linearly adsorbed species, and there is a bridge-bonded species. And in the case of rhodium, if the catalyst is prepared under proper conditions, you can also have what are referred to as isolated rhodium-1 species, which are characterized by two CO molecules bound to apparently isolated atoms. That doesn't give you very much information, because what it says is that, good, you can have a bridge, but is it a bridge between these two sites, between these two sites? When you have linear frequencies, is it really just an average over all the sites? Which sites are populated first, which sites are populated last? And that even becomes a question when you're working down in the regime where you want to have isolated carbon monoxides. If you put one carbon monoxide on this particle, where does it go? Well, what I'd like to do is I'd like to show you that ethylene absorbs in two different forms at low temperatures on noble metal clusters, and that they exhibit different types of chemistry from one another, and that's relatively independent. Also, I'd like to show that the relative importance of the pi kind or the di-sigma bonded type of ethylene, it depends on both the type of metal and the crystallite size of the particular metal that you're using. Now, thus far, most of the work that we've done has been on platinum, and so I'll begin really by taking you through step by step the evidence that we have that I think suggests all of these things. And then I would also like to, at the end, begin showing you some of the work that we've extended to with other kinds of important catalytic metals. Finally, what else I think is important here and is really a touchstone with Allied Signal's connection here is that it really is an opportunity to use a different kind of probe molecule for looking at a real technical catalyst. If you have carbon monoxide, the infrared absorbance of carbon monoxide absorbed on these supported metals is just incredibly strong. It's a very easy experiment to do. And traditionally, people have shied away from looking at other kinds of molecules on supported metals because you typically have very low concentrations of the metal, the supports can be strongly absorbing, and that the infrared intensities are very weak. However, I think that you will see that you can get very good signal to noise, you can get very useful information by using an alternative molecule. As a way of introduction, I'd like to sort of introduce you all to the family of ethylene species that one observes on supported metals. It doesn't include some of the kinds of things that you see on single crystal surfaces, and the reason that those are left out is because we have as yet not really observed those. The two principal forms of unreacted ethylene that one finds are pi-bonded ethylene, where the double bond character of the molecule is very clearly retained, and a second type, which is apparently a disigma-bonded variety, where you have now formed two carbon, platinum, or rhodium, or whatever types of bonds potentially, and you've lost this double bond character. The way in which we identify these species is shown by the variety of stretches that one can observe. For the pi-bonded species, there is a large number of symmetric and asymmetric CH stretching modes. There is a very strong 1200 wave number band in the carbon-carbon stretching region, and in CH scissoring type of motion, where you have in the pi bond, where you have the hydrogens swinging toward one another, you have also a relatively strong band. The problem one to observe at times is the disigma-bonded species, because there are really only two bands that one can characteristically observe. One of these is in the CH stretch region, and it sits between one of the strongest bands of the pi-bonded species and the very strong CH ethylidine bands. So this is really the most prominent band, and often when you have low concentrations of material, the CH stretching region is very difficult to detect anything with any appreciable accuracy. There is another very small band whose assignment is not really clear, and unfortunately, if we could go further down in frequency, there should be a very, very strong carbon-carbon band. But the problem is that for most supports, alumina, silica, zeolites, when you get down below about 1,000 wave numbers, things get very, very dark on you in a hurry, and you lose those bands. So the way in which we're going to be identifying these species is on the basis of these assignments. And I'll show you here what such a spectrum looks like. This is a 3 weight percent platinum on alumina catalyst. It's prepared in such a way as all the catalysts are, so that the dispersion is either what I would call moderate, measured dispersions of about 60%, or higher, so that we're dealing with relatively small particles, and we're also dealing with distributions of particles that are relatively narrow. And that way we can say with some confidence that we're looking at specific size classes of the supported particles. What's labeled here is the pi bands. As you can see, it's a very strong band. Here's an ethylidine band at 1339. This was done at 180 Kelvin. And the reason that we had to go to 180 Kelvin is that if you do the absorption at room temperature, what you find is only the pi bands or the ethylidine band. And so what that suggests is that you're going to have conversion of one of these species into the ethylidine as you warm up. Let me go on further. All of the spectra that I will be showing you are broken up into these two categories, from about 1050 to about 1500 wave numbers, and also 2750 to 3150, because that incorporates those strong bands that we can easily identify. So here you see the strong CH stretching band from the disigma-bonded species, and you can see right on the shoulder here some formation of ethylidine, and also here there's an ethylidine-related band. So what I'd like to do now is show you how these two different principal species, the disigma and the pi-bonded species, undergo different kinds of chemistry initially on the platinum surface. Specifically, disigma is found to convert exclusively to ethylidine as you warm the catalyst up. There appears to be no participation by pi-bonded, either as feeding into the sites that will slowly deplete the pi-bonded species and raise the amount of ethylidine that you form. It doesn't seem to come off the particles. It doesn't seem to interfere with what the disigma-bonded species is doing at all. Now, related to that then is that what we find is that we can change the strength with which the pi-bonded species adheres to a platinum particle just in the way in which we pre-treat the molecule, pre-treat the catalyst. And while we do that, while we observe these changes, again now, the ethylidine, or the disigma-bonded species, appears to be operating completely independently. It seems to be just a spectator as we change the chemistry of the pi-bonded. What I have here is a time-lapse collection of spectra at 180 Kelvin, and as you can see, the bands that are not changing are those that are related to the pi-bonded ethylene. The very strong 1203 band, there's really no change at all. Same with the 1498 band. Out in here, there's some changes due to differences in the removal of the background, but by and large, these bands are unaffected. However, as you can see, the 2912 band, due to the disigma-bonded ethylene, is decreasing, and at the same time, the bands due to the formation of ethylidine are growing in. And you can see that across the entire spectrum. This is this region here, this 1426, where there are actually probably 3 overlapping contributions. And you can see that a little bit of the edge here is beginning to grow in. Now what this suggests to us is that not only it's fine to be able to observe it, but it suggests that we might be able to learn a little bit more about the nature of the interaction between the disigma bonded ethylene, the ethylene, and the platinum substrate. And the most obvious thing that almost any chemist is going to want to do is going to be able to want to make these measurements at a variety of temperatures and see if we can determine an activation energy. And if you do that, it can be done. You can make measurements between about 170 Kelvin and up to about 230 Kelvin, where the process begins to go so fast that you can't really monitor adequately. But what you can see is you can, in fact, determine an activation energy for this process, and the activation energy is about 2.3 kcals per mole. Now, what I'd like to point out about this is that there have, to my knowledge, recently been up to 3 different determinations for the activation energy for ethylene formation on platinum 111 single crystals. And in all cases, while there is some variability in the exact numbers that one obtains, depending upon the coverage of the ethylene prior to letting it convert to ethylene, the numbers tend to be about on the order of 10 kcals per mole, not the low number of 2.3 kcals per mole. So this appears to be some effect, whether it's a metal support effect, whether it's a particle cluster size effect, we don't know, but it's a clear indication that for this particular transformation, ethylene and ethylene have different energetics on a supported small platinum cluster than they do on a large single crystalline surface. Well, let's move on and ask ourselves what happens to pi bonded. Now, if we take the initially saturated layer, these are all saturated layers, by the way, the initially saturated layer all the way from low temperature up to room temperature, we can watch the conversion of the disigma bonded species to ethylene, and we can watch the pi bonded just sit there. It just does not do anything. However, it does do something very interesting if you change the way in which you prepare the catalyst. And what I have here is initially the catalyst in its initial manufacture is reduced at 500 degrees, so that any lower temperatures that we subject the catalyst to should not change particle distributions or anything like that. What I have here are 2 different very simple sequences that one would go through in preparing the catalyst to begin to make measurements. We would evacuate in order to remove all the water and all the excess things from the sample cell, as well from the catalyst surface. And in one case, we would heat to 563 Kelvin. 563 is about the range of temperatures that have been used previously in activating these kinds of catalysts. We saw no real reason to go at any higher temperature. So we then expose it to H2 in a static case. We can vary the pressure between 10 torr, 400 torr. It doesn't seem to make a whole lot of difference. You then evacuate for about half an hour under those conditions, cool the sample down to whatever temperature you'd like, absorb the ethylene and see what happens. Alternatively, you can heat to a slightly higher temperature. And then you can go through exactly the same sequence of steps, so that the only real difference here is the temperature to which the catalyst is heated prior to the exposure to hydrogen, and consequently the temperature at which the evacuation is being done. Superimposed here are 2 different sets of spectra taken following those 2 different pre-treatments. In one case, can we have that focused a little better so we can see this? This is 290 centigrade. That would be the lower temperature. Down here is 350 degrees. And this is done with about 130 millitorr of ethylene present in the cell. Now, what you can see again, you can see the very strong bands through the pi bonded ethylene. You can see the bands, in this case, due to ethylene, because we were doing the exposure at room temperature, so the disigma bonded has converted completely. And you can see some small bands. For example, here's a very sharp band. There are some wings in here. And that is due to the residual gas phase ethylene that's still in the cell. Now, the reason I show this is to show you that these 2 spectra at this point are essentially identical. You can lay them on top of one another, and there is really very minor differences between the 2. It clearly demonstrates that all of the sites responsible for forming the pi bonded species are there. Equivalently, the numbers of ethylene that you form at this point are virtually identical. You would say that the particles, for all intents and purposes, are exactly the same. Your interpretation of these results, however, changes once you evacuate the cell to remove the excess ethylene. This is done at 290 degrees, and what you find is when you remove the excess ethylene in the gas phase, all of your pi bonded peaks just plain disappear. They disappear as fast as you can hope to look at the spectrum. Now this spectrum down here is now what we would consider a spectrum that was consistent with the literature up until recently. A number of researchers have looked at supported supported platinum catalyst using ethylene, using somewhat higher concentration platinum catalyst. But following evacuation, pretreatments at this temperature, what they find is that only ethylene remains. And this spectrum is in very good agreement with those results. As you might expect, I wouldn't be going through this if something else didn't happen after you did the higher temperature treatment. Again, up here is the spectrum with all the gas phase ethylene present. And as you can see, when you evacuate, lo and behold, the pi-bonded bands are by and large retained. Some of these differences in intensity in here are due to the gas phase ethylene that you've now removed. You can also see that there is a slight increase in the amount of ethylene that's present. And we think that that's due to just a reorganization of the surface layer as we remove the excess ethylene that was in equilibrium with the gas phase. But what we have now is we have, again, an indication that the pi-bonded species appears to be sensitive to these pretreatment conditions, whereas the ethylene, or the sites that are responsible for forming ethylene, are unperturbed. They're unaffected, at least as far as this type of measurement goes, in responding to this different pretreatment. So what we have now is we have two different kinds of sites. We have two different kinds of sites that do different kinds of chemistry, and they appear to do these different kinds of chemistry independently from one another. So getting back to our picture, what can we say about these sites, and how can we manipulate the catalyst in order to learn more about them? Well, if we follow the lead of the single crystal literature, what we would say is that, good, ethylene is being formed on these surfaces that have this threefold type symmetry, the 1-1-1 type faces. And perhaps the pi bondeds are being formed on the edges, perhaps on these other square symmetry sites. We haven't even said anything about what happens at the support interface. And for example, John Lowe from UOP has a poster discussing a possible explanation for the difference in the behavior of these two things, simply on the basis of which platinum atoms are in contact with the support and which ones are not. One way we can try to see how different things can be made is by changing the particle size, because if you change the particle size, you should change the relative population of the surfaces versus the edges versus the number of platinum atoms that are in contact with the support. That's fine and good. The problem is, what you'd like to have is something that's really well characterized. And generally, methods for preparing larger sized particles are not very well documented. You can indeed take this material, sinter it, and make it much larger. But in doing so, you always run the risk of having a tail of the distribution down to lower particle sizes. And if you then calculate the apparent surface area, which is what you're going to be sensitive to here, a very large fraction of the total signal you observe may in fact be due to those unconverted smaller particles. So that's not a very satisfying place to start. As I mentioned, the materials that we began with had dispersions of about 0.6. And what you can do is you can make the platinum particles smaller. You can go to unit dispersion. And if you do that, you do indeed see a change in the relative contributions of the disigma-bonded and the pi-bonded species. What we have here, this is a catalyst containing 3 weight % platinum. Average diameter is about 19 angstroms, and I assure you we've done almost everything we can to make sure that indeed that's the size of these particles. In the same sense, what we have here is a 1% platinum catalyst. And if someone could move his shoulder there, these particles are less than 9 angstroms, is what we believe. They exhibit unit dispersion by any kind of dispersion measurement that you would want to make. Direct observation with TEM, we were unable to observe any particles whatsoever. And what you can see is, sort of as you might expect, as you decrease the population of the planar types of sites, increase the relative amount of the edge sites, the relative amount of the disigma-bonded species decreases relative to the pi-bonded species. At this point, you can be brave. You can thermally abuse one of these catalysts at 800 degrees for many hours, make the population of particles tend to go toward the larger size, and if you do that, you do indeed see under those conditions, under room temperature absorption conditions, exclusively ethylene, you're unable to detect any pi-bonded ethylene whatsoever. So this lends some support to the idea that indeed the pi-bonded species may in fact be being formed at the edges between those planes, and the ethylene is being formed on specific planar surfaces. With all that in mind, what we can do now is we can begin to extend this work to other kinds of supportive metals. What I have here is some results for rhodium, for iridium, for palladium, and again, the platinum catalyst. And these were all prepared to have identical, or as nearly identical as possible, weight loadings and particle sizes. Again, the particle sizes are around between 15 and 20 angstroms on the average. Again, samples were prepared so as that in the spectrometer, in the beam, you have about the same number of sites, the same number of clusters. And what I'd like to point out is that the strength of the ethylene bands, at least this particular ethylene band, is nearly constant throughout this series. What's interesting is that the relative population of the pi-bonded species is different. And not only is it different, your ability to detect it is different. Whereas the 1200 wave number band is very strong. On the platinum catalyst, it's virtually absent. On the palladium catalyst, however, you can see some of the CH stretchings. You'll notice that this is enhanced by a factor of 5 over the rest of these. So on palladium, we indeed do have the pi-bonded species, but for some reason their spectra are not nearly as intense. Rhodium, on the other hand, exhibits features exclusively related to the ethylene. And again, these rhodium particles are sufficiently large that you have planes, but you should also still have those sites between the planes where you might expect the pi-bonded species to form. They just do not seem to want to form on the rhodium catalyst. I'd also like to point out that this deviates again from what's in the literature, and the reason it deviates is because all these catalysts were pretreated at a higher temperature. So that effect of pretreatment temperature on the stability of the pi-bonded, for example, pi-bonded had not been previously observed on palladium at all. It does appear to be not simply a consequence of the fact that we were using platinum. And as was pointed out in today's plenary lecture, there were pi-bonded species left on the platinum silica catalyst, and I would be very curious to find out if it's a support effect. So it opens an opportunity for looking at these metals on a variety of different supports. As in the case of the platinum, as I already showed you, you can go ahead and use these strong ethylene bands to measure activation energies for the conversion. Even though you can't see the disigma bonded species in some cases, you can definitely see the pi-bonded grow in. And what's shown here is that the palladium has an activation energy that's not too different from the platinum. However, the rhodium really likes to make ethylene. It makes it very, very rapidly at very low temperatures, and that's reflected in the very low activation energy for this process. So what I hope that I've showed you this morning is that we can use infrared spectroscopy of adsorbed ethylene, and that it provides a new and alternative view of supported metals. But the method is sufficiently sensitive to study many kinds of technical catalysts. I think that the 1% platinum catalyst that I showed you, the signal to noise there is quite adequate, and that you can probably go to considerably lower weight loadings and still get very good spectrum. And then finally, that there are site-selective properties that you can observe with ethylene as a probe molecule, and it would be interesting to try to exploit this. Thank you very much.
Thank you very much, Heinz. Vladimir?
Vanuit Leiden, Netherlands. In experiments in which the group of Shepard showed that ethylene is indeed responsible for certain peaks, the intensity of the peaks at about 1113 and something was measured by peak heights almost the same. In all your cases except of iridium, it was always that the CC bond was much smaller in size, and with palladium was that CC bond even not visible. We experienced with palladium a similar case, and actually BB and Yates also observed the same. They explain it by ethylene, but I wonder if it is possible that the CC bond, the absorption which we ascribe to the CC bond, would vary in such very, very broad range of intensities. Isn't it possible that there is another species next to ethylene, for example, ethylene?
That certainly has been proposed. The best argument that we can make against that is that if you do a very careful time evolution experiment, what you see is that all those peaks grow in relative intensity at exactly the same time. So that if you were forming two different species, those species would have to be formed in exact concert. And we don't think that that's the case. Now, you see different things on single crystals. I'm aware of that. However, it's not something that we've really looked at with a lot of intensity, largely because it's a very difficult set of experiments to do. We have observed, for example, just as Professor Domesic showed this morning, additional bands when you put hydrogen in, and notably absent from my list of metals that had been done previously was ruthenium. For example, on the ruthenium catalyst that we've made, we do not observe ethylene at all, whereas Yates does, and we think it may have something to do with the way in which we're pre-treating the catalyst, or it may have something to do with our size distributions. So yeah, there is the possibility that there are other species there, but up until this point, everything that we have, I think, really leads us to believe that all those bands come in concert due to one species.
Dr. Joyner?
You see differences as a result of really a comparatively small difference in temperature. I wonder if this can be due to the fact, do you prepare your catalysts by chloride route?
All of the platinum catalysts have indeed been prepared by chloride route. That's correct.
Do you have any evidence as to the different levels of chlorine has between the two temperatures? Because it would be tempting to relate high-bonded species to non-zero valent platinum, whereas of course the ethylene species is seen on single crystals and therefore directly related to zero valent.
Correct. Well, the non-zero valent platinum explanation of these, for example, that is the crux of John Lowe's poster. The catalysts, in terms of their chloride content, must be identical, simply because of the way in which they were prepared initially. Initially, the catalysts were reduced for 4 hours at 500 degrees. And what you're seeing then at lower temperatures, unless you can convince me that following 4 hours at 500 degrees, marginal additional times at lower temperatures leads to this change in the chloride content, I think you would say that the chloride content is the same. That's number one. Number two is you can make the catalyst go back and forth. You take exactly the same catalyst, pre-treat it at low temperature, don't get any stable pi bonded, and then clean it off with hydrogen at room temperature, heat it back up. Or for that matter, you can take a catalyst that has been pre-treated in hydrogen only at the low temperature, and then evacuate it only to the higher temperature. That active evacuation leads to the strong pi bonding. So we don't think it's the removal of any chloride species.
Thank you very much.